All right, guys, we're gonna get started on homework number 4, and the name of it is Building Functional Relationships. That is not centered, but oh well. All right, so we're gonna continue where we left off in homework 3. We were working with absolute value equations, and now we're going to get into absolute value inequalities. And problem number 1 looks like this. It says absolute value of 2x minus 1 is less than 5. Okay, so the first thing I want to go back to and remember what we did here, right? So let me just rewind a little bit. Let's say this was, let's say this was the problem. It's not, but let's say this was the problem right here. 2x minus 1 equals 5. The absolute value of 2x minus 1 equals 5. Now, last week what we did was we split this up, right? And we said, okay, well, we're going to go ahead and say 2x minus 1 is equal to 5, and then also say 2x minus 1 is equal to negative 5 and solve for each. We split it up right there. And then we solved and did all that. So, I could continue to go from here. But I'm not going to, because what we're going to do is we're going to move forward with this problem, and I'll rewrite it once again. The absolute value of 2x minus 1 is less than 5. Notice that this symbol is not an equal symbol. So what do we do if we're using an inequality and it's not an equation? Well, the way I would write this, if I wanted to continue, I would say negative 5. Remember how we turned this number into a negative before? Well, with an inequality, we're just going to say negative 5 is less than 2x minus 1, which is less than 5. Now, you might be asking why we actually did that. Well, I could also write it like this, right? I could, if I really wanted to, I could write it like this. I could say 2x minus 1 is greater than negative 5. Break it that way, and then also break it another way and say 2x minus 1 is less than 5. But really, if you look at it, it's the same exact thing. You just have to actually flip this sign around. So I've combined these two together into one, and it's easier to solve this way. So we're going to continue like this over here. Don't worry about doing it this way. You could if you really wanted to, but we're not going to do it that way. So what I'm going to do here, in order to solve this, now that I have my negative 5 on the left and my positive 5 on the right, the way I know this is negative 5 over here is I just take whatever numbers here and make it negative and throw it over there on the left. So I say negative 5 is less than 2x minus 1, which is less than 5. So what I want to do is, if I want to get rid of this 1 in the middle, all right, and I want to add 1, I have to add 1 to everything, right? To the left, to the middle, and to the right. And once you do that, negative 5 plus 1 is negative 4. This gives me 2x, and 5 plus 1 is 6. Now I want to get x by itself, so I divide everything by 2. And that gives me negative 2 is less than x, which is less than 3. Okay, so the first thing it asked was to solve the inequality. For all and inequalities, we're going to solve this way. And the way that we know that this is an and inequality is because the sign faces that way. So the less than or greater to will always be and inequalities. We'll talk about or inequalities next. But whenever you see the symbol less than and then also less than or equal to, those are called and inequalities. All right, so now that we're this far, it says we have to graph the solution as well. The way I would graph it is on a number line. Okay, so I'm going to go ahead and say like negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, and you can continue going. All right, so I say -2 is less than, okay, so I need to use an open circle. If you remember from last lesson, last week, whenever we dealt with these symbols, a less than or greater than symbol, we had an open circle. Okay, and then all the values that are, whoops, somehow I got the eraser up there. All the values, you know, x is between -2 and all the way over to 3. Okay, so x is going to fall somewhere between these values. X could be 1, x could be 0, x could be -1.2, x could be -1.7, whatever number falls between -2 and 3. Okay, and then I also graphed my solution down here. So that would be the answer for number 1. Now that we know how to do that, the next one will be a little easier. All right, so the next one, number 2, we have, whoops, we have 3 times the absolute value of y minus 9 is less than 27. All right, so now we can't actually do what we need to until we do something about this 3 over here. Now we have 3 times the absolute value of y minus 9. The opposite of multiplication is division. So I'm going to divide each side by 3 here. And that will leave me the absolute value of y minus 9 is less than 9. Okay, and now the way I would solve an and inequality, whoops, I know that because I have a less than symbol, so I know it's an and. So I'm going to say, instead of 9 in the end here, I'm going to start off with -9 is less than y minus 9, which is less than 9. Okay, and I threw a -9 out in front just because that is the negative version of 9. Okay, and now I'm going to go ahead and solve, add 9 to the left, the middle, and all the way on the right of this inequality. And I get -9 plus 9 is 0. All right, 0 is less than y, which is less than 9 plus 9, which is 18. Okay, now we have to graph this. So I don't know why these lines are making like this. All right, so let's say this is -2, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm just counting by 2s, right? So all the values that are between 0 and 18. And once again, this is going to be an open circle. I would use a closed circle if I used less than or equal to or greater than or equal to. And then 18 is going to be an open circle over here, and all the values in between would work. All right, all these values. So like 6 would work, 8 would work, 10 would work, 9, 7. Even though I count by 2s, even the odd numbers would work. And also decimals, right? So any number between 0 and 18, and that's how I would graph it. Okay. Now we're going to solve an OR inequality. And the way that I know I'm dealing with an OR inequality is going to be using either a greater than or a greater than or equal to symbol. Okay, so the way I'm going to do this is I'm going to just write the problem. The absolute value of x plus 3 is greater than 9. Okay, so the way I would solve this is, since I have an OR inequality, it'll be a little different from solving an AND inequality. So I'm going to break this in 2 ways. I'm going to say x plus 3 is less than negative 9. I flipped the sign and added a negative, okay? And then I'm just going to write x plus 3 is greater than 9. Make sure that, if I just had my equation, I would just set it negative 9, but you have to flip the inequality as well when you do an OR inequality. So we flipped the sign. Notice this sign moved to this, and the 9 moved to a negative 9. Okay? So now let's go through and solve each of these. Remember, these are OR inequalities. I'm going to go ahead and subtract 3 from each side and get x is less than negative 12, or subtract 3 from each side and you get x is greater than 6. Okay, and now that we've gotten this far, we are going to graph it. And let me draw my number line here. And let's just say I start with negative 14, negative 12, negative 10, negative 8. And I continue to number this. As long as you keep a consistent pattern, like I'm just using even numbers here, but you can use any numbers that you want. All right, so all the values that are less than negative 12, so I'm going to have an open circle, and all the values that are less than, so all the way to negative infinity, so I have to cover that arrow. And then all the values that are greater than 6, so I'm going to have an open circle here, and all the values that are greater than 6, all the way to infinity, so I include that arrow. Okay, so notice the difference between an AND inequality and an OR inequality is that AND, notice up here, what I just colored in, they are facing the same direction and they're inclusive there. Now the OR could go either to the left or to the right, and there's a bunch of values in between here that just don't work. They don't satisfy that inequality. So you can always go back and check it. So for example, let's look at this. Our original problem, the absolute value of x plus 3 is greater than 9. If I substitute in, let's say I substitute in 8. 8 plus 3 is 11. The absolute value of 11 is 11, and 11 is greater than 9. Okay? And I could go through and substitute any value that's actually on here, and it would work. So you can always go back and check and make sure you've done it correctly. Even up here in the very top example, on number 2 up here, you could go through and substitute in any values between 0 and 18. You can use this right here, this number line that we graphed on, in order to try any of those values. Okay? So we're going to go ahead and move on to number 4 and do one more OR inequality. All right. So number 4. Number 4 says 3 times the absolute value of 2x minus 1 is greater than or equal to 21. All right, so first, before I split anything, I want to get it where this 3 is not involved in this inequality whatsoever. So I'm going to divide each side by 3, and I get the absolute value of 2x minus 1 is, I don't know why it does that, is greater than or equal to 7. Okay, now this is where I split in 2 different directions here, and I can say 2x minus 1 is less than or equal to negative 7. Remember, I flipped the sign and I made that a negative number. Okay. And then what I want to do is I want to write 2x minus 1 is greater than or equal to 7. Okay. So from here, I'm going to go ahead and add 1 to each side, and I get 2x is less than or equal to negative 6. And I divide each side by 2, and I get x is less than or equal to negative 3. And then on this one, I'm going to add 1 to each side, and I get 2x is greater than or equal to 6. Divide each side by 2, and I get x is greater than or equal to 3. All right, so now if I wanted to graph this, I'll go ahead and make my number line, and I'll put 0 in the middle. And I'll say -1, -2, -3, whoops, -3, -4, 1, 2, 3, 4, and you could just continue going if you got room. But all the values that are x is less than or equal to -3. So all the values that are less than, so notice that the arrow points that way, right? So I'm going to use a closed circle because a less than or equal to or greater than or equal to uses a closed circle. And all the values that are less than or equal to -3, less than or equal to -3. And then I want to focus on this, the values that are greater than or equal to 3. So a closed circle for greater than or equal to in order to graph it. And then all the values that are greater than. And once again, I could check my work and try any one of these values and substitute them into our original inequality up there and make sure it works. All right, moving on. Number 5. Okay, so number 5 says represent the data using each of the following. So we're gonna have to add a few things, and I'll just letter them, right? I'll say A. We're gonna have to use a mapping diagram. We're going to need ordered pairs, and we're going to need a graph, and it says on a coordinate plane. Awesome. So we've actually done all of these before back in Algebra 1, but this is going to be a review just to show you what each of these are. So right now we are looking at a table in this problem. And there's really 4 ways to represent these relations. We're looking at a table of values right now in this problem that exists. And the table looks like this. We have 2001, 2002, 2003. And actually, it's split into 2, but we're going to combine them into 1 because it's the same exact thing. They just split them up into 2 tables for some reason, right? All right, so then each of these values coordinate with the number of inductees. So this was the year that people were inducted into the Rock and Roll Hall of Fame. 2001, they inducted 11 people. 2002, they inducted 8. I wonder what the process is to get inducted to the Rock and Roll Hall of Fame. 9 for 2003, 8, 7, 6. Looks like it's going down each year, right? All right, so that is called a table of values. Table of values. And they've given us a table of values, but there are 4 ways to represent these relationships. And we're moving on away from inequalities here into the next lesson. We're talking about relations and functions. And a big portion of chapter 2 will be talking about this kind of stuff. So this is our table of values, and it asks us to give us the 3 other ways to represent the relations. It's saying a mapping diagram. So a mapping diagram isn't very difficult. What I do is I take all my values on the left and I write them out. 2001, 2002, 2003, 2004, 2005, 2006. And then I just draw a little box around them, right? And then I take all my values that are on the right-hand side, so I can say 11, 8, 9. Notice that 8's already been used, so I'm not going to repeat it. 7 and 6. And then I'm just going to draw a box around that. Now, here's the easy part. All I do is draw arrows. So 2001 over here, 2001 coordinates with 11. 2002 coordinates with 8, as this table shows. 2003 was 9. 2004 was also 8. Right, so there's my arrow going up that way. 2005 was 7. 7, and 2006 was 6. It's being a little weird there. Okay, notice that 2002 and 2004 each go to the 8, and I didn't write multiple 8s, like I didn't have like an 8 down here, right? That's the way a mapping diagram would work. So you can see all the values that are on the left over here, right? And then you can see all the values are on the right. And you just have to draw lines mapping the two together. So that's called a mapping diagram. So I'll say mapping diagram. Not very difficult. You're usually already going to have the table of values, and then you move from there. Okay, you'll always have a piece of information. Like you'll have one of these relations, and then you have to create a mapping diagram or give me the ordered pairs. All right, so for the ordered pairs, that's just coming up with X and Y values, right? So my ordered pairs here, let me go ahead and move this over a little bit, right? My X and Y values. So my ordered pairs in this case would be 2001, 11, as I have over here, right? 2001, 11, and just follow that pattern. So have 2002, 8, 2003, 9, 2004, 8, 2005, 7, and 2006, 6. And once again, these are called ordered pairs. And then with ordered pairs, you can use these ordered pairs to actually graph on a coordinate plane. So we did a lot of graphing at the end of Algebra 1, some graphing in geometry, but a lot of graphing at the end of Algebra 1. We'll be doing a lot of graphing in this course. So you would create a graph, right? And this is what a coordinate plane looks like. Well, here's the problem with this. If I start off with with 1, 2, 3, 4, 5, and continue to go up, my X and Y values, if I create my X values are always my first value, right? So 2001, 2002, it would take forever until I actually got all the way into the 2000s, right? So we can, I don't want to say cheat, but we can almost skip a couple things in a way. And let me show you. I'm going to open up a new, bigger layer here that I can work with, all right? So this is just a continuation of number 5. So I'm just going to say 5 continued. All right, so let's say I draw my coordinate plane here. Not sure why it's doing that. All right, it's not the nicest graph, but it'll do. The way that I can kind of skip that in a way and make it so all of a sudden I can start with 2001 right here. What I can do is I can draw this little squiggly line, basically saying hey, look, I skipped a little bit part of this graph, and I'm gonna start at 2001, okay? And then 2002, 2003, 2004, 2005, 2006, 2007, and so on. Okay, so even into the future, we don't have data for 2007, but in 2007, if I were to look it up, we could find the Rock and Roll Hall of Fame and see how many people were inducted. Okay, and then my Y value, remember on a coordinate plane, all your X values are left to right, and my Y values are up and down. All right, so what I'm going to do here is I'm going to say this is 2, this is 4. You could number it however you wanted. 8, 10, 12, 14, and it just goes on. All right, so our ordered pairs that we had in our last one, right? We had 2001, 11. So I find 2001, which is my X value, and I go up 11, and I graph that point. That's about good right there. Okay, and then 2002, 8. So I go about there. 2003, 9. There you go. 2004 is 8 as well. All right, 2005 is 7. And 2006 was 6. It might not be perfect, but what this kind of looks like from a visual perspective, it looks like the numbers continuously go down. You can see that obviously by looking at the numbers, but sometimes that visual helps. Okay, and once again, this is just a graph using a coordinate plane. Whenever you see like this is called a coordinate plane, and you're going to graph on it. So remember that the x values always go first and the y values always come second. So my x values were listed on the left and my y values were listed on the right. And that's how you complete number 5. All right, number 6. It says determine whether each relation is a function. And it gives me a domain, and my domain was -9, 3, 5, and 11. And my range it gave me was -6, -2, 8, and 21. Okay, so what they did was they gave me a mapping diagram, and they just combined these two together and said, hey, look, we're going to go ahead and give you this, and we're going to show you that -9 correlates to -6. 3 also correlates to -6. 5 correlates to 21, and 11 goes to -2 and to 8. And the real question here is determine whether it is a function. Okay, so what is a function? So the way you can tell whether or not this is a function is that each x value, well, I guess rephrase that. I went back to my eraser here. Each x value should not be repeated. So in this case, my domain are all my x values and my range are all my y values. So notice that 11 is repeated. 11 goes to -2 and 11 goes to 8. Okay, which is something which can't happen. Now, -9 can go to -6 and and 3 can go to -6 as well. But if I have an x value, it should not be repeated, which means if I were to write out my ordered pairs right now, we have -9, -6, right? Then we have 3, -6, and then we have 5, 21, but then we have 11, -2, and 11, 8. Notice that it says each x value should not be repeated. So I have already a value, 11 is -2. I can't also have 11 be 8. My x values are the values listed on the left, and my y values are on the right. So I can't have this repeat. So since there is that repeat, this is not a function. Okay? So functions need to have unique x values. So I'll say a function has to have unique x values. They can't be repeated. All right, and we're going to move on to our next example. Number 7. All right, and number 7, we have 3, we have 5, we have 6, and we have 8, as well as we have -6, -2, 15, and 21. Okay, and the left over here is my domain, and on the right is my range. So whenever you hear domain, okay, these are all of my x values. And whenever you hear the word range, think these are all of my y values. Okay, and we have this mapping diagram. 3 goes down with 15 here, and then 5 goes with -2, and 6 goes with -6, and then 8 goes with 21. Now notice that none of my x values are repeated. If I were to write all my ordered pairs, I would have 3, 15, 5, -2, 6, -6, and 8, 21. Notice that all of my x values here are unique and they're not repeated. So this would be a function. Okay? If any of these x values over here were repeated, it would not be a function. Okay? So it's important to write them out. I like writing out the ordered pairs just to double check, just to make sure I'm not doing something silly. All right? The last one we're going to look at is number 8. And that gives me -14, -12, 1, and 3. And then -2, 15, 16, and 21. All right, so I'm going to draw a box around my domain and a box around my range. And -14 goes all the way to 16, -12 goes to 16 as well, still not a problem. But 1 goes to -2 and 1 goes to 21, that's definitely not going to end up well, right? So we know since this 1 gets split in 2 different directions, right, we can't have a repeat of our x values. So this is not a function. And just to check it, I can write them out, right? My ordered pairs, I have -14 that matched with 16, and then I had -12 went with 16 as well. Still not a problem, but the main problem is 1 going with -2 and 1 going with 21, 3 going with 15. Okay, the reason why it's not a function is I can't have 2 x values. I can have multiple y values, that's fine, right? But I can't have multiple x values. All right, so this is not a function. I guess it says can't have multiple x values. Can't have multiple x values that are the same. All right, that hopefully provides some clarity for you. All right, the vertical line test, number 9. Another way to tell whether or not a graph is a function, we just looked at the mapping diagram, but the way you can tell whether a graph is a function, you got this graph that kind of looks like this, right? That's what we're dealing with here. And it says use the vertical line test. This is so easy, and I feel like for some reason we have a problem at times understanding this, but the vertical line test, vertical means up and down, right? So all I do is draw a vertical line that goes through the function. And I see how many times when I drew this line, how many times it actually go through this graph. Well, it went through 1 and it went through twice, right? 1 time and then a 2nd time. Now, here's the problem. The vertical line test says that if it only passes through 1 time, only then it's a function. But if more than 1, then it's not a function. Okay, so this word function is being thrown around. We're going to be talking about functions all school year. Okay, so how many times does this vertical line that I drew, right? How many times does this go through the function? It goes through 1, 2 times. So it only passed through once? No, it's not. It can't be a function. So it is not a function. And that's how you would do the vertical line test. It's as simple as just drawing a vertical line straight up and down. And how many times does it pass through? If it only passes through once, it's a function. If it passes through multiple times, then it's not a function. Okay, so number 10, you've kind of got a graph that looks like this. Awesome. If I just draw a line anywhere, right? I don't care. Whoops. It has to be a straight line. That's not very straight. Let's say this is a straight line, right? If I draw this line, how many times does it pass through this function? Well, it only passes through one time. So it's a function. And number 11, we'll do one more. And here's one. The line kind of moves like this, right? So if I do my vertical line test, and I just draw a straight line going down, right? So this is my line. How many times does it pass through? Only pass through one time. So this is also a function. All right, only a few more here. We're moving on to number 12. All right, number 12 says evaluate each function for the given value of x and write the input x and output f of x as an ordered pair. Now, those instructions might seem kind of confusing, and that's why I just want you to look at the problem in this case. So, you see the problem? It looks like this. F of x, and you might be like, what in the world is f of x? I'll explain in a second. Be patient, and we'll get to it. And then over here it says 4x is equal to 4. All right, so let me break this down. Math sometimes likes to be confusing, and we like to be able to simplify things, but in the process of simplifying things, sometimes the reasoning behind it doesn't always make sense to us right away. Later on, the further that you move through math and the pre-calc and maybe even calculus, you'll see f of x used a lot instead of y. Right? So you could write this like this. You could say y is equal to 17x plus 3. But throughout Algebra 2, very often, you'll see f of x equals 17x plus 3. So whenever you see f of x, whenever you see something that says f of x, just think that's the same exact thing, same as y. Okay? So this is the same thing as this. All right, so as we move forward throughout and we learn new things, we'll kind of learn the why later on. Right now, we're really focused on the what. But what we want to do is we want to be able to find out, all right, what does the value of x equals 4, how do I solve this? So think about it this way. If I were to just say y is equal to 17x plus 3, and then x is equal to 4, solve, right? You could just go through and substitute in 4, right? You say, oh, well, y is equal to 17. Well, that value of x that I had is 4, so I'm going to add 4 there and multiply, right? And you would then from there multiply 17 times 4, which gives you 68. And you say y is equal to 68 plus 3, which gives you 71, right? So that's how you would normally solve that type of problem. Well, you're going to do the same exact thing for f of x. So what you would do is you would say f of, and x is 4, right? So f of 4 is equal to 17 times 4 plus 3. You'd say f of 4 is equal to 17 times 4, which is 68, plus 3. And then in the end, you get f of 4 is equal to 71. So in the very end here, the question asked, it said, evaluate each function for the given value, and then write the input x and output f of x as an ordered pair, okay? So we knew that this was our x value, and this is what it equaled in the end. So our final answer would be 471. That if I were to enter 4 into here in the very beginning, my answer would be 71. All right, so we have to get used to this. It might seem kind of weird at first, but it's not that bad. All right, so 13, we'll do again. We'll say f of x, which remember is just like writing y, so don't be afraid of it. There's nothing to be scared of. Is equal to, is equal to negative 2x plus 1 divided by 3. All right, and then it says for x is equal to negative 5. All right, so I would just say, all right, so I'm going to plug in negative 5 every time I see x. All right, so negative, okay, so 2 times negative 5 plus 1 over 3. And that's going to give me, if I multiply across, I get negative 10 plus 1 divided by 3. Okay, and then I go through a little bit more, and I get, I'm going to go ahead and just move from that line. Negative 10 plus 1 gives me negative 9, negative 9, and there was a negative out in front of there, excuse me. So negative 9 divided by 3. Negative 9 divided by 3 gives me a negative 3. And then negative 3 with a negative multiplying by a negative gives me 3. Okay, so that negative that's on the outside, you're going to have to multiply by, which gives you a positive 3. So if I were to go through and look at it, I started with f of negative 5, and I ended up with 3, which means my ordered pair which solves this is negative 5, 3. I can test it and go back through and make sure it works, but my answer is going to be negative 5, 3. All right, so make sure that when you're thinking of f of x, just think of that as y. All right, just think of that as y, being able to solve for y. And then you substitute this value in that they give you into here. They're always going to give you that value. You're not going to have to come up with this value in the top of your head. They're going to give you that value. All right, last two. It says for each function, determine whether y varies directly with x. If so, find the constant of variation and write the function rule. Okay, this is a good one. So starting off here, start talking about direct variation. And I have this table here, and it looks something like this. And remember when we first started, I think it was maybe one of the first lessons, we talked about like a process column of how you were to start here and how you finally got over to here. Right? Remember those process columns we made? Well, what this problem is basically saying is saying determine whether y varies directly with x. And basically what that says is, all right, when you start with 2 and you get 14, how did you get there? And you multiply by 7. You could say, well, you added by 12, but if you're looking through here, this is the same all the way through. That each of these you're multiplying by 7. So since all of these are the same, we could say that this varies directly. Thus, that's why we come up with direct variation. Okay, so we know that if we're doing the same exact thing for this one, and this one, that it varies directly. Now, if these numbers were different, right, let's say this was 2, 3, 5, and my answers were, my y values were like 14, 20, and then 25, right? Well, 2 times 7 would be 14, 3 times, I don't even know. It's not 7, right? And that's not 7. So we wouldn't say it actually varied directly. So this would not show direct variation. But in the problem that we're working with, number 14, this does show direct variation. So it's asking you to, if so, find the constant of variation. The constant, in this case, is 7. And the way that we would write a direct variation equation, the way it's kind of structured is y is equal to k times x. For direct variation, every time you hear the word direct variation, this is the equation that you just think of, okay? Which, really in this case, saying with all the y values that we get, okay, the way we get there is we take whatever the x value is and multiply it by 7. Okay, so going back up to this table up here, right, if you look at this table, if you were to say 7 times 2, you get 14. 7 times 3, you get 21. 7 times 5, you get 35. So that would be our constant of variation in this case would be k. Okay, our constant of variation, which is our constant that's not changing, that's 7. Whenever you hear something that's constant means it never changes. And variables change. Okay, so our 7 is our constant, and our variables x and y are there. And this is what they want for this problem, saying that any value of x that you get, right? So let's say I continue that, right? So let's say this is my xy table, right? So I got 14, 21, 35, right? I'm just rewriting what was already above. Let's say I wanted to add 6. That if I were to look in the future and try and think, all right, what would 6 give me? Well, that'd be as easy as saying, all right, 7 times 6, because that's my x value. 7 times 6 here gives me 42. Okay, so you come up with an equation, so that way later on down the road, we're able to add different values in there and still work with it. All right, let's look at number 15. It's the last one. And it says x, y. I have my x, y values. I have 3, 4, and 5. And I have 9, 10, and 11. Okay? So in this problem, it's going to be looking at my x values and seeing if they directly vary. And even though it looks like we're adding 1, 9, 10, 11, I can't really write a direct variation equation here. There's nothing that I'm multiplying by the same every time because I've multiplied by 3 here. 4 times 3, that's not the same. 5 times 3, that's 15, not 11, right? So as I look at this, if I were to write this is for direct variation, y is equal to k times x, there's really no constant. There's no direct variation, right? This is not the same each time that I look at it. So if I'm looking at multiplication there, it's not working. But if I were to add 6 each time, right, that would be a way to add it. But I'm looking more at multiplication through direct variation. Okay, so in this case, if you're looking at the problem, it says, for each function, determine whether y varies directly with x. So in this case, I can just say y does not vary directly with x because I can't write an equation that would give me a direct variation equation there. All right, so that's number 15. There is no direct variation there. If you have any questions, let me know.